In section 7.2, we're going to be discussing a technique called integration by parts, where U substitution was the reverse of doing the chain rule. Integration by parts is kind of the reverse of doing the product rule. We will use integration by parts to integrate a product, such as the product between a power function or an algebraic problem and a transcendental function. X times e to the x, x times sine x, x times log x, etc. So the product rule, the derivative of uv, hopefully we know this by now, is u prime v minus u, or plus uv prime. If you integrate both sides, you're going to get uv equals the integral of u prime v plus the integral of uv prime, or how we would want to write this is v du plus the integral of u dv. So if we rearrange, we're going to get the integral of u dv to be equal to u times v minus the integral of v du. And that right there is the integration by parts. The integral of u dv is equal to u times v minus the integral of v du. So let's do that with x times sine x. We're going to make one of these u and one of them v, or dv rather. So x is going to be our u, and dv is going to be equal to sine x dx. Now, one thing to keep in mind here is that it does matter which one you make u and which one you make dv. And I'm going to explain why after we've done the process. So, if we have u and dv, that means we need a du, which means the derivative of x, which is 1 times dx. So we're talking about differentials here. And v, which is equal to the antiderivative of sine x dx, which is negative cosine x. Now we're not going to worry about the plus c here. We'll put a plus c at the very end of the problem. All right, now if we use our formula, again we have the integral of u dv is equal to u times v minus the integral of v du. This becomes the integral of x sine x dx is equal to u times v, x times negative cosine x, minus the integral of v, which is negative cosine x, so we'll just change that to a plus, times du, and du is just dx. And the integral of cosine dx is really, really easy to solve. It's just negative x cosine x, and the integral of cosine is sine, so this is plus sine x. And here is where we'll put the plus c. Now, had we chosen u to be sine x and dv to be x, we run into a slight issue, because when we do du, that's easy. It's just cosine x dx. But when we do v, that's going to be 1/2 x squared plus c, or just 1/2 x squared. And u times v makes sense, but if I try to do the integral of v du, I've actually made the problem more complicated than what it started at. And that's going to be impossible to integrate, and we would have to keep going. So it's very important that you choose the correct u and the correct dv. So typically speaking, if one of the two factors, if one of the two functions that's being multiplied together in the integrand is going to differentiate to a constant eventually, that should be u. There's one exception to that case, and that the exception is if log x is involved in the problem. If log x is involved in the problem, regardless of anything else, log x is the u value. Otherwise, it's whichever one goes to a constant. Now, if neither of them go to a constant, then most of the time it doesn't matter. And we're going to see examples of all of these later on in the lesson. But for the most part, if one of the two factors does differentiate down to a constant, that's the one we want to set u equal to. Sometimes you have to repeat the process. So x squared e to the x dx. All right. So I know x squared is eventually going to go to a constant if we differentiate enough, so I'm going to let that be my u, which means dv is e to the x dx. du is equal to 2x dx. V is equal to the integral of e to the x, which is e to the x. And so if I write my formula down, I get this is equal to u times v, x squared e to the x, minus the integral of v du, 2x e to the x dx. Now I'm still not at a point where I can actually integrate that final integral symbol. So we're going to take this integral here, and we're going to do integration by parts with that. So in this case, u is equal to 2x, because I know that's going to go to a constant. dv is everything else, e to the x dx. If I differentiate u, I get 2 dx, and then for this, if I integrate this, I get e to the x. So this changes to x squared e to the x minus u times v, and I forgot my v here, 2x e to the x minus the integral of 2 e to the x dx. And I'm going to put the 2 out front just to make it a little bit nicer to look at. So I had my u times v again, and then the integral of this times this, v du. And so we end up with x squared e to the x minus 2x e to the x. This will become a plus because this negative and this negative cancel out, so plus 2, and the integral of e to the x is just e to the x plus c. Now, this is how you would be taught integration by parts in a college lecture class. But there is a quick way to do integration by parts that is taught only in a few books. And we're going to talk about it with the exact same problem we just solved, x squared e to the x. And some of the books refer to this as the tabular method. We have x squared e to the x, so we're going to have a u column, and we're going to have a v column. Now for the u column, we're going to be differentiating. For the v column, we're going to be integrating. So choose u and choose v the exact same way. So I'm going to choose u to be x squared. I'm going to choose v to be e to the x. Now I'm not going to include the dx here. It's not that big a deal. This is just the tabular method. So the derivative of x squared is going to be 2x. The derivative of 2x is 2, and the derivative of 2 is 0. And if you can, go all the way to 0 if possible. The integral of e to the x is e to the x. Integral of e to the x is e to the x. Integral of e to the x is e to the x. And we're going to stop at the same row where we have that 0. From here, we'll draw diagonal lines like so. And typically, you'll see this drawn with arrows. And then you'll see one arrow drawn backwards to the left on the bottom row. This backwards arrow is the integration arrow. You will only have one of them in the entire problem. Now, because of the way the formula works, uv minus the integral of v to u, all of your signs are going to flip-flop back and forth. And so what we end up with is x squared e to the x minus 2x e to the x plus 2 e to the x. And then you have a minus here, and it wants us to integrate 0. Well, the integral of 0 is just a constant, so we get plus c. And you'll notice that the exact same answer we got in the last problem with a lot less work shown or needed. For the most part, this is how I do all of my integration by parts. I never use the formula, but you may need to use the formula if you take a course that involves integration by parts in college. X squared log x dx. So as I said, most of the time we choose u to be the factor that will eventually differentiate to 0 or to a constant. But in this case, we have a log x, and as I said before, log x is our exception to that rule. So I'm just going to go to my u and v column. My u is going to be log x, as I have stated, and my v is going to be x squared. The derivative of log x is 1 over x, and the integral of v is 1/3 x cubed. Now at this point, we have two options. We can stop here, which is one of the recommended ways to do this, or we could do borrowing. And I'm going to show you both and show you just how we do this process. So I'm going to draw my arrows. This is a plus, this is a minus. So we're going to do 1/3 x cubed log x minus the integral of 1/3, and then x cubed times this 1 over x is going to be x squared. From here we would get 1/3 x cubed log x minus, and this would become 1/9 x cubed plus c. And that's a perfectly acceptable way to do this particular problem. There is an alternative way to doing this problem as well, and it's called borrowing. So I'm going to not do that. Get my eraser and erase all this. And the way that borrowing works, it's more like rearranging. I take everything on this bottom row and I can move it to either side of the u or v. The only thing I want to make sure I'm not doing is I don't want to move something, I don't want to switch places so that when I do the next step, I get what I started with. In other words, I don't want to put the 1 over x on the right side and the 1/3 x cubed on the left side and then do the process, because then I would be integrating 1 over x to get that log x on the top, and I'd be differentiating 1/3 x cubed to get x squared, which is what I have on the top. So when we rearrange, we want to make sure that we're not just switching these two here. We don't want to switch those. We want to rearrange them. And so in this case, what I think is the easiest thing to do is I want to put my constant over here, because that's my goal, is to get to a constant. And my 1 over x, I'm going to move over to the right side, and it will cancel down to an x squared, because x cubed over x is x squared. Then I can do my next step. So anytime I've done this dotted line here, I haven't actually done any sort of calculus. I've just rearranged things algebraically. Now the derivative of 1/3 is 0, and the antiderivative of x squared is 1/3 x cubed, as we've already seen. So what does this do for us? Well, I'll draw my line right there. Now, one thing to keep in mind, I cannot draw a line here because I didn't do any calculus. So if you have a dotted line, you cannot cross the dotted line. So that means the next diagonal arrow I can draw is here, and then here we still alternate signs, plus, minus, plus. So we get 1/3 x cubed log x minus, and then the 1/3 times 1/3 is 1/9 x cubed, and then the integral of 0 is a constant, plus c. We get the exact same answer with just a little bit more work. It involves a little bit of rearrangement. But again, if you prefer the first way, if you just want to stop after one step, that's perfectly fine as well. And most problems that involve log x work exactly like this. If you have limits of integration, first integrate without them, and then we'll do the fundamental theorem with it. So we have x sine x dx. So my u is going to be x, my v is going to be sine x. The derivative of x is 1, then 0. Antiderivative of sine x is negative cosine x, and then negative sine x. Signs are very important here. Plus, minus, plus. So we're going to get negative x cosine x plus sine x plus a constant, because the integral of 0 would be a constant. But I'm going to stop here. And because this is a definite integral, we're going to go from 0 to pi over 2. Cosine of pi over 2 is 0, so we don't have to worry about that. But we have this sine of pi over 2, which is 1. Minus. Now, if I plug 0 in, I get 0 for the first term and 0 for the last term. So my answer for that integral is 1. E to the x cosine 2x. Now, if you notice, neither of these are going to go to 0. Neither of them will differentiate to a constant. So we're going to have to choose one side to be u and one side to be v. And it really doesn't matter. I'm going to choose cosine to be the u only because it has a 2x in it. If my e had had a 2x, I would have made that my u. And it's only because taking the derivative of that's a little bit easier than dealing with the integral, because the derivative is just going to be negative 2 sine 2x. Whereas if I had done the integral, it would have ended up being 1/2 sine 2x. So this eliminates using fractions. And then this is going to be e to the x. Now, since neither of them goes away, neither of them goes to a constant, neither of them goes to 0, how do we know when we're supposed to stop? And the answer is we want to stop when the entire row matches the original row. Now, we're not going to do any borrowing in this process. We want the top row to match the bottom row. The only thing that doesn't have to match is a constant coefficient. So if there are any numbers in the front, we don't have to worry about those. So for instance, if we were to integrate or differentiate this one more time, we would get negative 4 cosine 2x, and this would be e to the x. Now, except for that negative 4, the bottom row here, cosine 2x and e to the x, matches the top row here, cosine 2x, e to the x. And at that point, we're going to stop. And it may not make a lot of sense as to why we're stopping, but we're going to stop anyway. Drawing our arrows, plus, minus, plus. So we end up with the integral of e to the x cosine 2x dx equal to e to the x cosine 2x minus, or plus, because the negatives cancel, 2 e to the x sine 2x. And we have a minus the integral. I'm going to put the 4 in the front there, e to the x cosine 2x. All right. So it doesn't look like anything has improved, except if you treat this integral as its own variable, then it matches this entire integral over here, except on the right side we have 4 of them being subtracted. So if I bring the 4 on the right side over to the left side of the equation, we end up with 5 of these integrals. And we'll go ahead and put our plus c now anyway. And then the last step would just be to divide everything by 5. So the integral of e to the x cosine 2x dx is equal to 1/5 e to the x cosine 2x plus 2/5 e to the x sine x plus c divided by 5, which is still a constant, so we'll just call it plus c. And there you go. Now, you don't have to show all of those steps going through. I would have, if it was just me, I would have just skipped that middle step there completely, because I know when I bring 4 over here, I'm going to get 5 of them, so I can go ahead and just divide by 5 first, immediately, as we go. All right, then we have the integral of log x dx. Now, this one's not as obvious that it's an integration by parts problem, and the reason why it's not obvious is because there's only one factor in the integrand. So when we do this problem, remember that log x has to be our u, which means that dv has to be 1. It's the only option we have left. Log x times 1 is log x, and that matches my integrand right there. So the derivative of log x is 1 over x, and the antiderivative of 1 is x. Now at this point, we could stop or we could borrow. I'm going to go ahead and borrow. I'm going to bring the 1 over x over to the right side. That's going to leave me with a 1 over here. And when I bring 1 over x on the right side, 1 over x times x is also 1. Now the derivative of 1 is 0, and the antiderivative of 1 here is x. I have achieved 0, so I'm going to stop there. I can't cross the dotted lines. So plus minus plus gives me x log x minus x plus the integral of 0, which is a constant. So right here, this is the antiderivative of natural log x, which we were not able to get before now because we did not know integration by parts.